cutting-edge research in computer vision and natural language processing with a focus on deep learning transformers and large language models. So his academic journey includes a PhD in electrical engineering from IIT Kanpur and MTech from IIT Bombay. Before joining Microsoft, Dr. Patro held prestigious postdoctoral positions at KU Leuven, Belgium, and Google Research India, contributing to foundational advancements in AI. His industry experience spans roles at Samsung R&D, Harman International, and L&T, where he led engineering efforts across software and systems. Dr. Patro is a prolific contributor to the research community with publications in top-tier conferences such as CVPR, almost in all conferences, right? The world's best. CVPR, ICCV, NeurIPS, AAAI, all are star conferences. EMNLP, the best in the field of NLP, BMBC, WACV, Multimedia, SEM Multimedia, ICASP, and journals including transactional image processing, pattern recognition, neurocomputing. He actively serves as a reviewer for leading venues like CVPR, ICCV, ECCV, NeurIPS, ICLR, ACL, EMNLP, NACL. I mean, these are the top conferences in the field of natural language processing. And journals such as the TEEP transactions on pattern, PAMI, TIP, TMM, PR. He is a proud member of the CVF and ACL and is deeply committed to advancing the frontiers of AI research. So with this, now I request Dr. Badri to kindly start the session.
Thank you, Deepak, for the nice introduction. And is my screen is visible to all of you?
Yes. Yeah. It's visible. You are audible.
Yeah. Thank you. Thanks, Deepak. Thanks again. So today I will discuss something about beyond transformer model, like Simba. Just a minute. Simba. So I will discuss. I will start my slide from this. Like, just I'm getting call. Just a reason I'm little bit disturbed. So. Just give me a minute. Sorry, today is something like ITR. Everybody knows that. That's the reason we are getting calls and all. Hello.
Yeah. Today is the last date, but
Yeah.
I did it only yesterday night.
Right. So today I will discuss something about that how our model, the transformer based model, affect to our Gen I, the current Gen I era. So I'll start with this. This question is, tell me about PMs. This is the question I have. So the generative model is giving a response like the current Prime Minister of India, Narendra Modi. I didn't ask which country and all. It took my bias and try to generate this one. Then the model is not so good at all. Whatever the generative model, let's say it's a Chat GPT 543 or Plum or any Llama or anyways MTP or any model, GERK, doesn't matter to me, since it's given. It's a The model is not uh, uh, generative, means not a general model. I can't use it's a depend upon the country to country or the region to region. So same question, can I generate a image of current PM? Still I didn't give a uh, it's a language based problem. That problem exists in the image also. You can see this generate the Narendra Modi. So the third thing is what he is doing. So his gesture, who he means who is taking that from that uh, his gesture significance, that is emphasizing something important at that. So there is something bias. It is taken by both multimodal, unimodal, like vision, like language. How will you solve all these things? I, this is not related to the bias. The bias is taken care by the model is like that attention based model or a SSM based model. So the nice application of the Gen AI, so everybody knows that question answering, image generation, music, to generate a music, and also the videos, code generation, the GitHub pilot everybody is using for uh, nowadays. The coding is not a big problem. Everybody knows the coding. They know everything. Chat GPT or if you use GitHub Copilot, they know everything. So just give a context, they will write a code for you. Then data for the research, it's another nice application. What is data for the research? Like something like the airplane crashing. So such a data we don't have frequently. S- so we need to have that data. We need to generate that data. So to generate that data, so we required this generative model to do that. If my generative model is doing just a bias based data generation, since it is a Air India crash, so everything is based upon the Air India generate. So it's not, the model is not unified because it took a bias of Air India. So how will you solve whatever the data generative? See, the bias is not there. It impact to the generative model as well. So it will generate a images so that you will train based upon those images. So your model is completely biased toward a particular reason only. And the privacy preserving, definitely. If I will use let's say chat gpt for uh, NIT server or a banking like SBI banking, if the model is taking memorizing or data is there and people can extract data, then that's a very danger problem. You can extract my uh, account number, password, everything, then you can use my account. Just the banker, they don't know. They just use chat gpt or uh, any model to help them. But internally the model is taking the data, and whatever the data is there, from that data people can extract the private information to that. So these things, let's say I will use in my home. So if somebody will leak my data, can take my data, I will not give, just I gave a model. But nowadays people can steal data from the model. Just if you give a model bytes, they can generate a data from that, which the data from which the model is trained. So these are the things we need to take care of that. So current research is not like improving that. That is one part is there, improving transformer LLM based model. Also, how will you use this? These are the research direction. Now, right now the people are telling that next 10 to 20 years it's a completely AI. So AI is based upon these things. Whereas there is another one is the research aspect. How will you improve the model? It's a post processing. Before post processing, how will you improve the model? So yeah, just whatever the model we are using, there is a two types of model, like is a discriminative model and the generative model. The backbone is same, transformer. The encoder is same, the transformer. The decoder also a transformer, but for a discriminative you don't require decoder. Just you get a embedding from the encoder, means encoder transformer, then you try to classify it. For the generative model, just you have a decoder on it, try to generate a image or a text based upon that. So this is for that generative adversarial based generative diffusion model, VAE, then autoregressive. Uh, so diffusion, there are different types of that: image colorization, image generation, super resolution. So where we stand and what we will do in the next. So we start 2014 like that. VA is a VA and VQVA. This is the era where people were using VA, VQVA. Then same era, the GAN has came also. The GAN, pix to pix, cycle GAN, style GAN, and that. 2020, Google has come up with a transformer known as the Vision transformer. From that, people are jump into that. There are n number of the transformers are there. VIT is the first transformer. Day-8, cite any name you took, then there may be a transformer and specformer, spectral, all these things we are also having in that field. Also we come with the CBT, CMT. Then in our model we have a SBT, specformer. So these are the transformer era. Up to 2023, people are calling this is a transformer era in a vision. For generative model, it's the same. It's a latent diffusion model. Then the multimodal, the daily, ImGen, Midjourney. Then another things is like a stable diffusion model, uh, and instruct pix to pix is their control net, GPT-4. So today I will discuss something. Yeah, these are the application where we are working on it, at object recognition, segmentation, object detection, image generation, for text classification. So here it is like, if you generate one model, how can you make more generalized? Like let's say we did for the vision, can I use for the text classification, text generation, and also the other tasks like time series, forecasting, anomaly detection. These are the things. To do that, we start with a simple thing is like, uh, sequence to sequence model. Given an input sequence, we need to have an output sequence. This is a standard problem. It start from 1960. So there, from that day, the sequence modeling is there. People were using the sequence model, the syntax method, rule based method. Then they use a RNN, recurrent neural network, then LSTM. Then 2014 they come up with the attention based machine translation. The sequence to sequence people are using, given a one sequence, try to generate another sequence. Let's say given a sequence is English, try to generate Hindi or Odia, like the different things are there. So this is input sequence we need to map to the output sequence. So let's say in a continuous field, this is what my input, I need to have an output like that. I need to map it. So I will train enough data so that model will know the manifold of that and try to generate on it. As I discussed, there are different architectures are there: RNN based model, CNN based model, and most famous is the transformer based model. So uh, it's a very famous model. So the main problem, so yeah, CNN, RNN you can't parallelize. CNN you can easily parallelize, but you need to have a more context on it. So the transformer, it is easily trainable. Means trainable means you will make a parallelize, and uh, you can make a distributed system easily parallelized. So let's say you have 1,000 base size data, so ImageNet can be trained within 1 hour. You heard about that. That can be possible also. The H100, it is a huge one, so you can put parallelize all the batches and have a one 300 epoch you can do within a 1 hours. So that is the, I think I can tell that modularized the transformer is that. So it's a very easy and modularized. So the everybody is try to use this architecture. So what's the problem with that? Then if it is a very good and everything is there, then what's the problem? The problem is like n square. What is n square? The complexity is n square. Let's say I have a sentence of 512 tokens. The complexity means uh, time, number of computation required, that is much more. So can you reduce that complexity, n square complexity? It's a standard as a matrix multiplication, that is a n square matrix multiplication. So whatever the sequence you have, you will put one is a row form, another is the column form, then you find a correlation. A correlation is how much similarity and the relation between token 1 with token 2. So everybody know what's the core component of that. The transformer is like a uh, uh, two things. One is an encoder, another is a decoder. Encoder which represented text and decoder which generated text. What's the advantage of transformer? What is the disadvantage? One is like a computational perspective. But okay, let's say I don't have, I have a huge computation. I have a like supercomputer is there. So H100 is there. I don't bother about computation. So what's other advantage? The semantically, what's the advantage? So let's say if you want to go any of the previous value, you can jump into the transformer. Where the sequence model like the recurrent neural network, if you want to go hello, so from is to hello, you have to go is to name. The name, what is the relation between is and name? What is the relation between name and my? What is the relation between this? So you will compute all the relation, then you find, okay, how is related to hello. But in transformer, you just have a value. What is the uh, correlation between is and hello? It, since it is a matrix multiplication, the rows and the columns, if you want, I can tell that 1 2 3 4, 4 cross 4 matrix. It's a 0 means 1 cross 4. If you go to the matrix, zeroth row and the fourth column, that would be the value. That is the relation between is with hello. But in RNN, you can't go there. There is nothing like matrix multiplication there. So the is depend upon name, name is depend upon my is depend upon hello. This is what the biggest problem in the RNN architecture, and this is what the advantage of the transformer architecture. So you can see is depend upon. So in this matrix you can find these values. So, what are the different components of the transformer so that it is easy for us to get a state space model? So, different component is a feed forward neural network and multi-headed self-attention. And so here you can see the transformer training is very fast. Inference is so. Why training is fast? Because it stores the matrix. Whereas the inference, each time, each new word you will generate, you will make a new matrix. Let's say when my name is there, so you have a 2 cross 2 matrix. My name is there, you have a 3 cross 3 matrix to compute. My name is Martin is there, so you have a 4 cross 4. My name is Martin, some Patro is there, so you have a 5 cross 5 matrix. Like that, Martin Patro is studying an MNIT in computer science. So each time, each new word generated, the computation is going increases that many times. That's the reason the inference is very slow, since the scales quadratically with sequence length. So I discussed the RNN and the advantage and disadvantage. The transformer is training is fast, inference is slow. Where the RNN training is slow, we don't have any parallelize, we have a inference is fast. So can I combine these two and do something like that? So this is what the state space model. Let's say you have right now this position, you want to go this is a mess. So if you want from here to here, if you want to go, so what is that next potential next state is this one, this direction. Each each other each state you need to find what is the optimized way to go to exit. So what is that vector? The position and the distance from exit. How much distance? If I will go from here, the current state is x1 is 4 1 and the distance is 7. So this is what the state space matrix. So if I will go like this, or I will go like this, or I will go like this, that you need to find it out. This is what the state space model is there. It's not a new one, it's a very old technique. Everybody heard about that state space model and digital signal processing or digital electronics during the BTech. So it's the same kind of thing. It's derived from that mechanics in the state space. The system is there, so input is there, the output is there. So the how the input and output is related. Uh, so it's a very the theory is very big. So just I'm going through giving the grasp what is state space. So theoretical, it's have a very means well defined equations are there. There is a state equation which has a relation between the input and the output. The state equation has a relation with the input as well as the state matrix, and the output equation has a relation with that state versus the input. So how they are related to each other, I will show you. So this is what the state matrix, this is the state. So this is what that input matrix, this is the input. So let's say you first initialize that state, and you have a state, and you initialize this matrix. You each time you will update these A, B, C matrix. Also D is there, and C is a output matrix, how the input and output are related. And D is a sorry, input and state is related. D is a matrix where is like a residual system, how input and output are related. So basically we need to learn A, B, C, D. These are the parameters we need to learn it. So basically this is the state space model. So x time B plus h time A, whatever the state you will get, multiply with C, you will get a Y, which also depend upon the D times X. This is what h time A, x time B, and whatever the output you will get after this solving this, you multiply with the output matrix with the residual this. So this is in matrix form of SSM, how it looks like. So, like input multiply with input matrix, you will get output. The state with the state matrix, you will get output. You will add it, multiply with C. After that, you will also add the residual term. You will get a final out. The main thing is to you need to learn A, B, C. D also. D people basically, if you don't put any residual, you make it D to 0. Just you need to learn A, B, C. These are the steps how you will compute uh, this. So D is just a skip connection on it. So since it's a basically it's a continuous signal, you need to make a discretized form of A and discretized form of B, and after that you will learn this one. So you have a delta, you have a matrix, you need to find a exponential, then you need to find a inverse and complete a B, then you will multiply with that. So there are lots more theories there. Just I'm skipping. I'm giving the overall view of what is a state space model and how it is represent recurrent way of modeling state space. And this is a convolutional way. Initially, h0, which is the b times x0. Similarly, y equal to c times h0. Y0 is equal to c times b into x0. Then you will get h1. H1 is this equation like the previous one, b time a time h0 plus b time x1. Then you put h0 from here, like that you will substitute all this thing. Finally you will get a equation of k which is depend upon c times a to power k b b into x0, c times a to power k minus 1, like that. It is nothing but you need to learn a you need to learn a kernel of abc. Then after that you will put a it's just like a convolutional property. So input convolutional with this kernel, you will get a output. So you need to learn this kernel. So how will you learn this kernel? That is what main things are there. So these are the convolutional representation is there. So uh, just it is a shifting then multiplying with input. So like that, first is cb is there, cab is there. Now you just shifted by 1, then you multiply, then you will get again you shifted by 2, then you like that you will shift how many watts are there. So this is what the they used convolutional, because training time we need a fast, so they use a convolutional way of training, and during inference they use a recurrent way of thing. So there are n number of state space model, hippo, oh, then Mamba. Mamba is the latest one. Hippo is there. Hyena is there. Then there is mongoose are there. Lots more things are there. So for uh, for time being, I'm leaving these issues and just uh, I'm telling how will you use for the vision task, and what's the efficient way of using this into the vision task is like given an image we need to classify into the top 5 category. Let's say it's a ssm model, it's a lion, it's a saint, I mean whatever you want to do it, but our objective is the model should do the uh, less number of parameter, computational efficient, and give a better feature representation. So the main problem I have discussed is the uh, dot product matrix multiplication. So the transformer, the vision transformer, what they do, they inherit the language transformer. After that they are adding the patch embedding. What is patch embedding? They each patch, what is this patch? They divide the images into the different patches. For each patch they put some number, so that they can able to identify this patch is belongs to this position, this patch is belongs to this position. To that they need to have that. So the architecture is same, multi-headed self-attention and mlp with a residual connection. So main problem is here. So computational complexity increases quadratically, then transformer having a issue of long sequence. So the what is that long sequence? Uh, as I discussed that if you increase number of the tokens, the performance is going degrading. So this is what demonstrated by Day-8 and Mamba, Mamba. Like if you increases number of the tokens, the performance is drastically decreasing. Top one accuracy is decreasing. Here also they are showing the resolution is 512, 640. If you increase the resolution, means number of the token will going increases, then it is the computational GPU memory is increasing, flops is increasing, performance is decreasing. So how will you solve that one? So yeah, in order to solve, uh, we have some paper where we are using that scattering vision transformer. We have used something like spectformer, removing attention with a spectral layer that will make more efficient. But is that solution is enough? No, because if you see the uh, spectral transformer, the Fourier transform, the complexity is n log n. Still you need to have some better complexity. N log n is, it is less than n square, but we need to have something the linear complexity. If I will have something like linear complexity, then well and good, okay, I can do something on it. Then another problem I discuss, people are start using vmamba. Here the vmamba is there. So the vmamba, the problem, what's the vmamba problem? The Mamba has a stability issue. Stability issue is the training loss is not converging. When you have a high resolution images and the number of the token will increase, uh, then the model is diverging. Diverging means it will give an n value on it. So oh, why there are n number of factor, you have seen that ABC matrix. ABC matrix, there are inverse is present, there is a logarithm term is present, log of something negative kind, then also it will fail, and also the inverse is there, so that also uh, ill problem, that may occur the ill problem. So how will you solve that one? So this may result to NN problem or the menacing gradient and exploring gradient. So to do that, we have something like uh, uh, we everybody knows that the signal and system Oppenheim book. So linear system, linear state space model exhibit stability when all the eigenvalue of a matrix are the negative. If you have a negative real number, so e to power minus of minus that become e to power minus lambda that become goes and uh, decreasing, right? So that become converging. Did you get the point? If my eigenvalues are negative, then the my problem is solved. E to power minus lambda, then that is converging. So it's the linear state space model is stable. Then you have to have find the eigenvalue and do stability. Finding eigenvalue is not so easy because you need to have them again the same process for that matrix multiplication is there an eigenvalue. So how will you do some efficient way of finding eigenvalue? I need to use state space model. I need to have some efficient way of getting eigenvalue so that the convergence issue of Mamba will solve and the finding eigenvalue complexity that will also solve. To do that, we come up with a technique is Einstein uh, for fast Fourier transform for channel modeling, and Mamba we are using. Mamba is using Fourier transform. Uh, Mamba is for that sequence modeling, in FFT for the channel modeling. So addressing the stability issue of Mamba using the Fourier transform with a non-linearity model to get a Eisen values of the non-negative real number. So this is what we did. Simba architecture use a Mamba optimized Mamba architecture. It combines ineffective for channel modeling, Mamba for token mixing. So this is for RNN. Everybody knows that. Then ComNet, VZZ, ResNet, and all transformer, VIT, and all. Then Mamba, we come with a architecture. I will discuss about that architecture. You can see that people are using MLP here for the channel mixing. They are using that attention spectral mixing, MLP mixing, Mamba, Hyena, Hippo, S4 for the sequence mixing. But our model, we combine that Mamba. So if you see the V Mamba and other architecture, they don't have anything about the channel mixing. So we introduce a channel mixing to the Mamba architecture to solve the instability problem. That is what our contribution. We introduce a channel mixing technique to the Mamba architecture to solve the instability problem. So how will you do that? So there is different combinations are there. So the combinations are that INFFT and Mamba is known as the Simba. So here you can see Mamba is the Mamba which is there in that. Then we have a INFFT. INFFT is Einstein fast Fourier transform. Just input. Then we have a fast Fourier transform. Since this fast Fourier transform is a non-parametric, we convert to the parametric form. Then make it the complex form, and we start to multiplying. So multiplication is not so easy because it's a fast Fourier transform. If you have a sequence length and the channel dimension, that many dimension required for that. So if my sequence length is increasing, my complexity is also going to be increased because that many parameter is going to increase. Because when you convert non-parametric to the parametric, we need to have a complete uh, model so that it have a sequence parameter as well as the channel parameter. To solve that, that is basically known as a tensor blending method, tensor mixing or a tensor blending. To solve that, we come up with a Einstein blending or a Einstein mixing. So what is that? We divided. So we have taken this concept from our newspaper, that is SBT, for the reference. Uh, so here there we used Einstein matrix multiplication. We inspired from that and we divided the channel into block diagonal matrix. So we have a block, we have a diagonal, then just that many parameters are required, and whatever uh, the input is there, height and width, and the channel is divided to block and diagonal. Then we required a block diagonal times diagonal parameter, just this many parameter. It is independent of H and W. It is independent of your sequence. Whatever your sequence is, that doesn't matter. Just we have a something on that uh, channel mixing on that. If you have this uh, parameter, uh, then we are much more efficient way of multiplying, because just we multiply this two and we'll get a performance like that. But for that we just require a very small parameter which is visualized in the slide. uh, so this is the sequence mixing and the channel mixing. So these are that calculating ABC, which is there in the code. How will you calculate this kernel? How will you make more efficient in the kernel? So model is SSM, local convolutional, and the gated network. And this is that convolutional theory. This is the relate theory. this is basic things so we need to update is like uh, the Einstein tensor blending, as I discussed, it depend upon the height and width. So the number of the parameter is height and width and the channels. This many parameters are the required. Whereas Einstein blending, it's a more efficient. You can see the size of it is independent of height and breadth. Just we have a C, and the C is also very small. We divided C times B times CD times CD. So this many parameters are required. When you multiply that, you will get the same performance and the better performance that we prove that we have a better performance on it. So what's that frequency domain channel mixing? We come up with that. Okay, this is what the frequency domain channel mixing is there. So this is Einstein multiplication. This is uh, Einstein matrix multiplication. We in that real domain, in the imaginary domain, then we combine it. Since the first Fourier transform is in complex form, we need to have a complex form. Then whatever the EMM is nothing but that input multiply with the weight and we'll get the output. This is what the formula is. So each layer is having this much. So we have a two layer in FFT, Einstein matrix multiplication. Then after that we have a IFFT on it. So this is complete how this channel mixing is done. Then how this code is happening in the channel mixing form. The complete things are present here. Then we will go to the data. So to train this, we used ImageNet data set. We are having the 1200K for the training data and the 50K for the test data. Then we have a CFAR 110. We fine tune it for the transfer learning case. Then also we have a flower data set and the Stanford car data set we did for transfer learning. So as a result, you can see Simba is doing good performance. Simba small, Simba base and Simba large is doing better performance across the all the Mamba based model, and the results are here. You can see with a very small parameter, 15 point K, you will get a 81, 36.6, you will get a 84. With very small parameter, very less computation, less parameter, you will get a performance, better performance. So if you want very less parameter and less computational, the Simba is the best model to do that. So we tried different abelian analysis, only uh, SSM, only different kinds of SSM. These are the performance we are getting. Different kind SSM plus MLP, we are getting that. When you have a Mamba with INFFT, Mamba with MLP, Mamba with monads, we are getting like that. We validated for the small model. So then we did a transfer learning. It is trained on a ImageNet data set and fine tune on different data set like CFAR, CFAR 110, flower and car data set. We are going similar to that, not beating, but it is most likely the whatever the diet performance is there, and the model is doing most nearly to that with a very less number of parameter. This is what the Simba is for the task learning in a different task like instance segmentation task. We are getting that. So these are the training parameter you can have that. So this is all I'm having for that Simba. If you have any question, please let me know.
Yeah, participants, if you are having any queries on Simba and state space models, right? Whatever Dr. Badri has discussed today. So probably, I mean, from this talk, what at least you can learn is like what exactly is these architectures, and then you can go through the literature and explore how people have applied this kind of technique to solve a wide range of NLP as well as computer vision task.
Yeah, so the code and the paper is also available in a GitHub and Google Scholar. You can refer that.
Yeah, yeah, there's a question, sir. Can we apply this model to any classification task or its application dependent?
No, you can. It's a transformer architecture. You can apply to the any classification task just for any data set like CFAR data set and 10 CFAR 10 or 100. Just the last layer you need to fine tune it. So it's like 512 or a 768 to 10 or a 768 to 100 or a 768 to 20, 30, any number of the classes that linear layer you can fine tune it based upon your task and it will work. Yeah, so we are corporate world. We are not, means we can release our code, but wait, sir, we can't release it.
Yeah, so I think there is one more query. So, can Mambas be used for video understanding?
Definitely, you can use for the video understanding. So Mamba directly you we can't use because there is some issues are there. So for video understanding, like for the Simba case, you can use Simba for the video one. There is some video Mamba is there. One paper is there, video Mamba. You can use for video understanding also.
Is pre-trained version is available?
Yeah, I told that pre-train is not available. Code is available.
Yeah. So, Aditi, I have tried reproducing results of Mamba model, but
Yeah.
while training, it was giving NAN for image enhancement task. Okay.
Yeah, that is what the Simba is there because it's a instability is there in computer vision task. Mamba is trained on a NLP based task. When you train in the vision based task, you are getting NN problem. So to solve that one, we come up with a technique is known as the Simba. Mamba you can use for that sequence modeling. For the channel modeling you can use for in FFT.
Mm, what is state space model? What is the role signal
Yeah,
processing in it?
yeah. The state space model is like a given. It's just a, you can see the recursive or a feedback system is there. That is what the signal processing system. It's a linear continuous time domain signal is there. So how will you make optimized or stable in a linear system? If you go through the signals and system or a digital signal processing, there is a stability in the system, continuous time domain signal. If you want to find a stability, then you can do this. So open humming is there, proakis is there, digital signal processing. You can refer to that as well.
Yeah. Any other queries from the participants? Yeah, there is one question from Sweta. Can you explain channel multiplication?
Yeah, definitely. Channel multiplication, you can see. See, this is what my channels are there, right? So here, height and width. Let's say you can completely take this as a sequences or a patches, and these are the channels are there. 512 channels are there. So what I did, I split this channel to the two part. One is CB times CD. So C is equal to
Correct.
CB times CD. So if you divided this CB times CD, that is what my total number of the channel. So what I did, CB times CD, I extended to the 3D to have a matrix multiplication, tensor multiplication. The tensor multiplication, directly I'm not multiplying one to one, that is element wise multiplication. I use a technique known as the Einstein matrix multiplication. In Einstein matrix multiplication, what it is that, so if you have uh, n equal to n CB times CD and you have a weight CB times CD, so if you multiply these two matrix, you will get n times CB times CD. So n is nothing but a h cross w. So you will get a same matrix if you multiply these two. See, the input is also divided this. The matrix is this. You multiply this. These two only multiplied, and final output you will get like this. Did you get the channels? Hello.
Yeah, I think. Yeah, Dr. Sweta, I think. Yeah, yeah. Any other queries? Yeah. So the Simba paper is published. Yeah, it is still archived.
It's there in the journal, so it's an under process.
Okay. I mean, it has been communicated to journal, but it
Yeah,
is available on archive, right?
archive it is available.
Hmm. Yeah, I think there are no other queries from the participants. Participants, if you are having any queries, you can also drop an email to Dr. Badri. So whenever he will get time, so he'll get back to you. So thank you very much, Dr. Badri, for
Thank you.
sharing your insightful knowledge, right, on a very recent topic known as state space model and a couple of variants of the state space models, especially useful in the field of computer vision, like Vision Mamba you explained. I mean,
Yeah.
like Simba and all, which can be easily adapted to solve many computer vision problems. So I, on behalf of Computer Science and Engineering Department, the E and ICT Academy of MNIT Jaipur, right, thank you
Thank
to
you.
accept our request and sharing your valuable time with us.
Thank you, Deepak. Thank
Yeah,
you all.
thank you very
Nice.
much.
Bye.
So yeah, okay, bye. Yeah, so participants will be having our next session on generative models, especially generative adversarial networks, right? Which will be delivered by Dr. Ashish Kumar Tripathi from NIT Jaipur. There will be one hands-on session also. He'll be talking about both the theory and especially what are deep generative models and